Welcome to an introduction to acid-base equilibria. Before diving right in, let's review a few things about acid and base strength. Recall that weak acids and weak bases are those that dissociate less than 5% when dissolved in water. Conversely, strong acids and strong bases dissociate nearly 100% in water. Instead of memorizing the strength of every acid, we can just remember one rule. If an acid isn't strong, it's weak. This comes in handy since there are only 7 strong acids that we need to know. Strong acids include hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, chloric acid, and perchloric acid. These strong acids will burn your skin. They can also burn through clothes. Always exercise extreme safety and caution when working with them. Like acids of bases, we can say, if a base isn't strong, it's weak. For this class, we're going to use the term strong base for any alkali hydroxide or alkaline earth hydroxide. So if we see hydroxide with any element from the first or second group in the periodic table, it is a strong base. The strong bases we'll see most in this class are potassium hydroxide and sodium hydroxide. Strong bases can burn your skin and cause blindness if mishandled. Again, always exercise extreme caution and safety when working with them. We know that the term strong means that a substance dissociates almost completely in water, but it does not tell us anything about how much dissociation acid or base undergoes. So, how do we quantify the strength of an acid or a base? Think back to general equilibrium constants. The constant for any reaction in equilibrium is the product of the concentrations of the products, each raised to the power of their coefficients, divided by the product of the concentrations of the reactants, raised to the power of their coefficients. Just like the general equilibrium constant, acids and bases also have a constant expression, and this is what quantifies their dissociation. Let's take the dissociation of a general acid HA. This acid, when placed into water, will dissociate into its individual ions, H+ and A-, also both in the aqueous phase. The dissociation constant for acids is written as a capital K with a subscript of lowercase a. We express this as the concentration of H+ raised to the power of its coefficient times the concentration of A- raised to the power of its coefficient, all over the concentration of the acid, HA, raised to the power of its coefficient. A general equation and expression can likewise be written for bases, only the dissociation constant for the bases is written with a subscript of lowercase b. And of course, we're using a base rather than an acid. There are 2 things to note. Number 1. Although we know that weak acids and bases will only partially dissociate, we can still express their dissociation in this way, since acid and base strength depend on concentration. Number 2. Always know the identity of the substance in question. That is, know whether it is an acid or a base. Recall that acids are proton donors, while bases are proton acceptors. This becomes very important later on in acid-base equilibria. Stay tuned for what's next in the acid-base equilibria series.